Now that we have talked about single random variables, we have talked about functions of single random variables, pairs of random variables, functions of pairs of random variables, it's time to take this to the upper level and talk about vectors of random variables. So consider the vector x equals x1, x2, dot, 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 xn transpose of random variables. The joint PDF is f x1, x2, dot, 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 xn of x1, x2, dot, 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 xn. To marginalize fx1 of x1, for example, is integral on x2, x3, dot, 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 up to xn, fx1, x2, dot, 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 xn of x1, x2 to xn, dx2, dx3, dxn. So two quick things about the notation first, and then we continue. I mean, we are writing on board. This is not LaTeX, so I don't really have the luxury of writing bold X. So the symbol I will use for the vector is this underline. Sometimes I will make mistakes, obviously, so you understand what we want to do. And the default type of vector we have in this course is a column vector. So when we transpose it, it becomes a row vector. So when we write X transpose, it becomes a row vector. X is a column vector. All right? So now we are talking about the joint PDF and the marginalization of functions of vectors of random variables. So we have a vector of random variables, x2, x1, up to xn. This is the joint PDF that describes how they work together. It's function of all of them, and it has all the values they can take. In addition to that, we can marginalize by making the integration over all the other variables except the variable we are seeking. It's pretty much very, very, very close to what we have already seen for pairs of random variables. Now, let's define some quantities. Mx is the expected value of x1, the expected value of x2, dot, 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 the expected value of xn transpose, and it is called the mean vector. And then we have Rx is this big matrix, the expected value of x1, x2, the expected value of that, this is x1 squared, the expected value of x1, x2, dot, 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 expected value of x1, xn, the expected value of x2, x1, the expected value of x2 squared, dot, 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 expected value of x2, xn, and then expected value of xn, x1, the expected value of xn, x2, up to the expected value of xn squared. And this is called the correlation matrix. And we also have kx that I will write in a different format than the one you have in your notes in order to minimize the writing, to be honest. It is the variance of x1, covariance x1, x2, dot, 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 covariance x1, xn, covariance x2, x1, variance x2, dot, 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 covariance x2, xn, and then you have covariance xn, x1, covariance xn, x2, up to covariance, up to variance xn. And this is called the covariance matrix. All right, some important observations about these matrices. What can you say about this matrix and this matrix? from the properties of matrices immediately? They have the same dimensions. They have the same dimensions, that's correct. What else can you say about this? Both of them are symmetric, right? Both of them are symmetric matrices. So they are both symmetric matrices. Also consider this following matrix X transpose. Okay? What is the rank of this matrix? What is the rank of the matrix X transpose? Who said 1? This is a rank 1 matrix, right? XX transpose is a rank 1 matrix. It's just the first row, and then you have different scaled versions of the first row. Essentially, if you look here and you remove the expectation, you can get the second row immediately by multiplying x2 over x1, right? And so on and so forth going down, right? Okay, good. So if we consider this matrix, do you have any problem if we write Rx as the expected value of X transpose? Do you have any problem with that? There's absolutely nothing. And then we can also write the covariance Kx as the expected value of X minus Mx, X minus Mx transpose. This is the expected value of X transpose. And then, what is the next term? Can someone tell me what is the next term here? So you have, the last term is obvious, Mx transpose, right? But then what are the terms you have here? There are two more terms as a result of this expectation of multiplication. Yeah, right? So minus Mx, expected value of X transpose, minus expected value of X, Mx transpose. What is this? It is Mx transpose, correct, and another one, and a third one. So the final answer will be that Kx is, what is this? We just wrote it here. It is Rx minus Mx transpose. This is the relation between the covariance matrix and the correlation matrix. Is this relation reminding you of anything we have seen for two random variables? How could you get the correlation from the covariance, or the covariance from the correlation? Even for the variance, yeah, I could think about it this way. But here in that context, in the context of covariance from correlation, you get the covariance of two random variables from the correlation of the two random variables by subtracting the expected value of X times the expected value of Y, right? So it's just a matrix form over multiple random variables of something we have already seen for two random variables, right? Okay, let's do an example. We have X, that is X1, X2, X3 transpose. And here we have Fx1, X2, X3 being e to the minus x1 squared plus x2 squared minus square root 2 x1, x2 plus x3 squared over 2. divided by 2 pi over square root pi. And we are required to find mx, the mean vector, and the covariance matrix kx. How could we think about a problem of that form? How could we think about a problem that looks like that? Yeah, but integrating something like this is a very hard task. So you try to match it to something you already know. What's up? That's a good first step. They will all end up being Gaussians. That is correct. But what type of Gaussian? For example, if we look at x3, do we have any joint terms having x3 and x2 multiplied, or x3 and x1 multiplied? No, right? So we can actually separate x3 on its own. x3 will be independent from the other two. And then for x1 and x2, there is obviously a term combining them, square root 2x1, x2. So what should we try to match this whole thing with x1 and x2 with? So we said all of them will be Gaussian. That will be separated. So the remaining ones will be joint, right? So we try to match this combo to the joint PDF of two Gaussian random variables, okay? So let's try to rewrite this based on all the points we just discussed. We can write this as E minus x1 squared plus x2 squared minus 2, 1 over square root 2 x1 x2 divided by 2 pi 1, 1 square root 1 minus 1 over square root 2 squared. Remember the term square root 1 minus rho squared. Do you remember that term from the jointly Gaussian PDF? That's why we are writing this in that form. And then we will have another quite simple term, x3 squared over 2 above the exponential divided by square root 2 pi times 1. Now, what can we say about x3 immediately from here? It is Gaussian 0, 1, exactly, normal distribution 0, 1. We can write this as fxy of x and y, fx1 and x2, for that matter, x1 and x2 of x1 and x2, and that is fx3 of x3. How about x1 and x2? Jointly Gaussians. What are the variances? What is sigma x1? What is sigma x2? Exactly, both of them are 1s. And rho x1, x2 is 1 over square root 2. But because the variances are 1s, this is the covariance of x1 and x2 immediately. Right? Okay? So now, can someone help me by telling me what mx will be? It's zeros everywhere, right? It's zeros everywhere. You don't have a single term having x1 with no power 2 or x2 or x3. You don't have a single term of that shape. If you had, you would have tried to complete a square to get the mean, but you don't. So mx is 0 directly. Can someone help me with kx? What should we write on the diagonal of kx? What should we write here? Yeah, ones, right? These are all the variances, so 1, 1, 1. What should we write here? What's up? Exactly. Thank you. 1 over square root 2, and this one is 1 over square root 2. How about the remaining terms? The zeros everywhere, right? Because x3 is independent and thus uncorrelated from the other ones. Do you have any questions until now? Go ahead.
I don't understand how mx is 0.
So remember that for the Gaussian, you have this. Right? That's what you have as the PDF of a Gaussian random variable with some mean and subvariance. In order to have a non-zero mean, you got to have some term that has x in it. You don't have any one. The only term you have had x1, x2, and this is just a covariance / correlation term. Example 2, let's do another example. So we have x has known mx and kx, and we have y equals ax, a deterministic. So this is not a multiplication of two random variables, and we want to find my and ky. Is the problem setup clear? Okay. Let's write this matrix A. So we have y being a11, a12, a1n, a21, a22, a2n, an1, an2, ann, multiplied by x1, x2, up to xn. Let's try to write that also of the same form, y1, y2, yn. Okay, let's try to write yk in terms of these x's. Summation xi, I equals 1 to n. What should we put here? Someone needs to answer this. What should we put here? AKI, thank you so much. So should I say always someone needs to answer something? Okay. Open brackets, forget about probability, forget about all of this, and let's talk about something else. After we finish, we will close the bracket and return. That's what I want to do always, is to try to tell you things that go deeper than probability and signals and stuff like that, things that are more generic, that you can use in many, many situations. This particular equation, it represents the equation of any transform of a finite signal from a domain to a domain. Any transform, anything. The Fourier transform, the Hadamard transform, any transform you would think of. The only difference between a transform and another would be what is AKI. For example, think about the DFT. When you think about the DFT, you have a finite signal xn. This finite signal you put here, you multiply by coefficient. That coefficient is what? Just an exponential. That is function of the k and the n. And you are summing over the n, and you are getting the frequency domain component. When you think about the Hadamard transform, it is the same thing. You just remove AKI and replace it with whatever coefficient coming from the Hadamard transform. This is the equation of any transform. Any transform. You have one variable, and you have a signal that is finite. For example, in time or in any domain, not necessarily the time domain, you are multiplying by coefficient, you are summing over the variable specifying the first signal, the time domain signal in Fourier transform to get the component in the other domain. All right? In simple terms, when you do the DFT, you could put all the exponentials here as well. You could put them in a matrix, and you could write it in a matrix form as well. Right? Remember that for the DFTs and for these types of transforms, if one signal goes from 1 to n, the other one also goes from 1 to n. Okay? So this is the equation of any transform, anything. It's just that you will need to specify a ki. All right? Close the brackets and return to this. Now, given this equation, when we enter the expected value, can we write it this way? Anybody's having any issue with writing it this way? There's no problem. Can that lead us immediately to EY as a function of EX? Exactly. It's just the coefficient matrix again. Right? And thus, we immediately got my equals a mx. The other thing we need to do is ky. Ky is the expected value of y minus my times y minus my transpose, which is the expected value of a x minus mx, x minus mx transpose a transpose, which is a times this big expectation that I'm not going to write again, a transpose. What is this? Under the expectation, what is this term? What's up? It is, yeah, it is the covariance matrix of x, exactly. This is exactly kx. We have it, right? So the final answer is a kx a transpose. Okay. Can someone relate this thing to someone we have already seen as well? For single random variables, just for single random variables, can someone relate this final answer we got to something we have already seen? The variance, exactly. The variance of what?
Function in one variable, it's base square, not matrix form.
Exactly, right? So if you have y, yeah, absolutely. So if you have y equals ax, that is what our friend here is saying, you end up having v of y equals a squared v of x. But this is the squaring in the language of matrices. All right? Everybody's okay with that? Great. Now we will move on to convergence, improbability, and sums of random variables. All right, so sums of random variables. So consider x1, x2, dot, 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 xn, IID random variables. And then we define the following quantities. Sn equals summation from I equals 1 to n xi. And mn equals 1 over n Sn, also defined as the sample mean. Before we move on, let's again look at the setup. What we have been discussing until now is a vector of random variables, but they can be anything. They can be dependent, they can be independent. Now we are talking particularly about x1, x2, xn. Not only are they independent, they are also identically distributed. This is what IID refers to, independent, identically distributed. You can see them as just samples of the same random variable. You have some random variable x and you are observing it at different times. Every single time you observe it, this is also a random variable that is a sample of the original random variables, and it is independent from the other samples, and all the samples are identically distributed. Okay? So we are defining a new random variables that is the sum of all of them. Anyway, we are defining after that the average of all of them by dividing over n. So that is the setup we have. The weak law of large numbers tells, weak law of large numbers, it tells that limit as n goes to infinity, the probability of mn minus mu becoming greater than epsilon is 1, less than epsilon is 1, where mu is the expected value of any of them. They are, remember, they are all IID. The strong law of large numbers says that the probability of limit as n goes to infinity, mn equals mu, is strictly 1. What are these two laws referring to? Let's think about it. First of all, do you see that the two of them refer to the same thing? So they say that mn converges in probability to mu. Right? As n goes to infinity. They both say the same thing. This format is the standard format in convergence. You have already seen it in convergence of sequences, convergence of series. This is a standard format. For sequences, for example, you say for each n there is epsilon, right? For each n there is epsilon, and this epsilon is getting smaller and smaller as more terms are into the mix, right? And this one is also telling the same thing, but this is a stronger law than this one because of two reasons. The first one is this is the probability of the limit, not the limit of the probability. So this is probability is 1. This gives you a sure statement, not a limit statement. So that's why this one is stronger than this one. Another reason is it doesn't have an epsilon. All right? It tells you that the probability of the limit will become 1 is surely 1, 100%. All right? So how to think about this from the perspective of a practical application? There are various ways, but we have already seen something like that in one of the lectures before when we were averaging over Bernoulli trials. Remember that? We did this together one time. It just tells that when you have these samples of your random variable and their number is large enough, you are summing over all of them, dividing by their total number, this surely, almost surely gives you the expectation of the random variable. So mn can be understood as, and we will talk on Thursday about estimators, can be understood as an estimator of mu. Okay? Everybody's okay with that? We also have the central limit theorem. And the theorem tells that if we construct a new random variable, Zn, which is Sn minus n mu over square root n sigma, again, sigma squared is the variance of xi, then the probability that Zn less than or equal to Z equals, or for that matter, since it is convergence, limit as n goes to infinity, this probability becomes 1 over square root 2 pi sigma integration from t equals minus infinity to z e to the minus t squared over 2 dt. What is this? Yeah, right? That is the CDF of a standard Gaussian, right? So this is fxs of z, and thus we can say that Zn is a standard Gaussian random variable in probability as n goes to infinity. Before we give examples, we got to stop in front of this a little bit because this is mind-boggling. We have some IID random variables that are copies of one random variable, and all of them, without an exception, are independent and identically distributed. All that we did is that we summed them up to create this Sn, and in order to get a zero mean unit variance random variable, we just subtracted by n mu and divided by square root n sigma. This is to make the mean 0, to make the variance 1. That's all what we did. Did we assume anything about the n random variables? Nothing. We didn't assume anything. This theorem is telling that when you do something like this, you end up getting a Gaussian random variable regardless. Just think about this. You have n random variables of any distribution, you are summing them, you're just making some normalization. Forget about the normalization. Leave this out. Forget about n mu and square root n sigma. Forget about them entirely. You know why they are there? They are there essentially because this is limit as n tends to infinity. You don't want to have an infinite mean random variable. So they are just to make the math work. Forget about what is there to make the math work. Think about the fundamental thing. So think about Sn alone. You're just summing some IIDs created from any distribution, and the result is a Gaussian. It's just magic, right? This is another reason why this particular random variable is called the normal random variable. Not only because of all these properties in real life that end up having actually normal distribution, but also because other phenomena being distributed differently, when you create n samples and sum them, they end up being normal as well. It's just something unbelievable, right? We will see an example on this, but let's first do an example on the law of large numbers. So we have x1, x2, up to xn are IID uniform in the interval 0 to pi over 2. And we want to find approximately the limit as n goes to infinity, 1 over n summation from I equals 1 to n cosine xi. Let's do the distribution first. If we assume that they are all copies of a random variable called x, what is this distribution? What should we put here? 2 over pi, right? Now, can someone tell me immediately what this limit will be? No, not the final answer. What this limit will be in terms of the calculations. Cosine? This will end up being cosine 2 over pi? No. In terms of calculations, don't try to think of a final answer. How can we deal with this? Given what we were just talking about. Yeah, thank you, exactly. It is the expectation, right? Next question, the expectation of what? Exactly, right, thank you. So this is the expectation of cosine x. Immediately using the law of large numbers, right? This is 1 over n, Sn, right? This is Sn, another Sn. That's the whole thing. This is some Sn, right? And Sn here, your random variables are y's. You can call them yi, where each one of these yi's is a cosine, right? So the answer is, it is the expectation. So this is the expectation of cosine x, which is the integral x from 0 to pi over 2, 2 over pi cosine x dx, which is 2 over pi sine x from x equals 0 to pi over 2, which is 2 over pi. It looks very complicated, limit 1 over n summation, but this is just 1 over n Sn, and this is just the expectation. Okay? Everybody's okay with that? So the last thing we will do together is we will try to demonstrate the central limit theorem through an example. So again, we have x1, x2, xn, iid uniform in 0, 1. And then we want to demonstrate, we demonstrate the central limit theorem as follows. So what we are going to do is that we will have random variable z1, z2, z3, and z4. And we would just make some substitutions. First of all, what is the expectation here? What is the expected value of x if they are all samples of x? What is the expected value? 1 over 2, exactly. What is the variance? 1 minus 0 squared over 12, 1 over 12. All right? Again, this is just we do in order that the math works. It really doesn't matter all that much. The concept is what matters. Okay? So our random variable z1 will be x1 minus half over 1 over square root 12. The second one will be x1 plus x2 minus 1, 1 over square root 6, right? Just adding another random variable and adjusting the scaling for the variance and the mean, right? And then you have summation from I equals 1 to 3, xi minus 3 over 2, divided by 1 over square root 4. And the last thing, summation from I equals 1 to 3, xi minus 2, this one is to 4, divided by 1 over square root 3. First of all, is everybody following these z's? What are they? How we are constructing them? Everything? All right? This one is the most simple, the simplest. So we have z1 f z1 of z1, and then we have z2 f z2 of z2, and then we have Z3, F Z3 of Z3, and then we have Z4, F Z4 of Z4. This thing looks like this, centralized around the 0. What will this thing look like? Triangle, right? That's what we exact. Why is that? x1 plus x2, summation of two random variables. They are independent random variables, convolution, right? Again, forget about these. I don't care. We just want to look at the shape. Now, what will happen next? It's a convolution between this and this. This convolution in terms of order will give you what? Constant, linear, what should come next? Quadratic, right? You expect it to give you something quadratic, right? So, indeed it will. It will give you something that looks like this. All right? How about the next one? It will be this one and this one again. It will start improving the Gaussian shape you have. We didn't do anything other than just, we had 4 samples. On the third sample, the Gaussian shape started to emerge. On the third one. So yeah, here, yeah, the math tells that it's the limit as n goes to infinity and all of that, and you got to make all this scaling, okay, fine. But the Gaussian shape will start to emerge immediately for the uniform random variable at the third summation. The fourth makes it a better Gaussian, the fifth makes it an even better, and so on and so forth, but the shape will start to show off immediately at the third. Immediately once you add the third term. There will be more advanced cases that it could be better if you do them in a MATLAB project, and possibly we will have a MATLAB project on the central limit theorem, but here we just did it theoretically, and we managed to see what is going on. All right? Anybody is having any questions about anything we discussed today? Go ahead. Why what has to go to infinity? Here you mean? For the law of large numbers?
I was thinking about the mu is the mean of x and all x's are identical. So it shouldn't be...
Aha, but here you are not taking the mean. This is very important. Okay, that's a good question. So let's illustrate it patiently. Here, if you are taking the mean, one sample suffices. You take a sample, E of xi is E of x is mu, problem solved. The problem here is the mean is a parameter that you do not know. And you have these samples and you want to assess the mean through the samples. That's the idea. Here you are not taking any expectation. This is Mn is 1 over n summation of random variables. You are not taking any expectation. This is just an averaging, a literal averaging, no multiplication by probability or anything here, right? And thus, this Mn is an estimator of the mean. You can estimate the mean through taking samples and averaging over them. Why can't you take 2 or 3? Because your estimator will be a bad estimator in that case. If you take 1, for example, you pick its value, it will never give you the expectation. Take the case of a discrete uniform that can take a value of 1 or minus 1. If you do it once, your result will be 1 or minus 1. How can that give you the mean? All right? So here you got to have n to go to infinity because here you just sum the samples and divide them by n. All right? I will see you on Wednesday.